As you may imagine by this point, SQL Server and Couchbase handle data types differently. By relying on JSON, Couchbase allows the essential data type of any field to be described, while leaving enforcement of that type up to the particular language and SDK in use, when type enforcement is actually needed to meet a functional requirement. Let's take a look at how JSON types compare with SQL servers. JSON delivers simplicity. Instead of 11 different ways to describe a number, JSON provides one, an unquoted numeric value, with or without relevant decimals. Should there be a real need for further distinction, virtually every programming language provides the ability. Strings are similarly simple. Instead of 8 varieties, any single or double-quoted value is interpretable as a string. JSON does support explicit booleans through the use of true and false as keywords. Date-time values are commonly encoded in JSON documents using the ISO 8601 format, though other options such as epoch time are supported also. Couchbase provides a thorough set of date-time support functions to flexibly parse and interpret data in this format, both in Nickel and our SDKs. Geospatial data for both nearest neighbor and spatial distance can also be encoded in JSON. Couchbase supports indexing and querying of geospatial data. So here's an interesting question. Is a missing field a data type? As we've seen, to support agile development, Couchbase emphasizes schematic flexibility through a set of logical statements in Nickel, which enable query filtering based on structure, such as whether a field is present in a particular document or not, or present but assigned as null. JSON also expands past traditionally scalar record values with flexible support for inline objects, arrays, and their nested combinations. Bracket-wrapped sets are interpreted as numerically indexed arrays, and brace-wrapped name-value pairs are interpreted as objects, and each JSON document is itself an object. All this makes it easy to support multidimensional data within a record when appropriate, such as embedding the geospatial data for a location without having to fuss with joining a lookup table. Of course, when and why it makes sense to embed multidimensional data rather than reference it, which one can also do with JSON and Couchbase, is part of the art of modeling data in JSON. Transaction support is where the differences between supporting systems of record versus systems of engagement become most apparent. SQL Server provides extensive support to ensure unquestionable transactional reliability, no matter the performance cost, which makes perfect sense for systems of record. Due to our complementary focus on high-volume, highly scalable systems of engagement, Couchbase historically provides a data modeling-focused approach to Atomicity. Now, architecturally, this all means SQL Server indexes are updated synchronously, while Couchbase index updates are asynchronous. SQL Server famously guarantees transactional completion or rollback of virtually any sequence of statements. Couchbase provides multi-document transaction support in version 6.5 and beyond. SQL Server therefore assures the atomicity of any transactionally identified set of updates to any number of tables, while Couchbase assures atomic updates at the level of individual documents. SQL Server supports either consistent or dirty reads. Couchbase key-value operations are always consistent, while the desired consistency of a Nickel query is configurable per request, as we'll see ahead. SQL Server isolates using pessimistic locking. Couchbase supports optimistic locking through check and set values in the metadata of every document. Couchbase architecture is memory first, so writes are immediately available to be read and are then persisted to disk. The SDK can confirm disk writes, and if necessary can also confirm when replication, if configured, has completed within the cluster. How SQL Server and Couchbase each handle atomic rights is a reflection of their fundamentally different approaches to data modeling. Few systems of record could be more significant than those managing financial transfers, such as moving funds from a savings account into a checking account. SQL Server's ability to guarantee the durable completion or rollback of such logically related operations is a core relational feature available for those operations requiring it. However, from another view, it's the fundamental inability of relational systems to gracefully handle hierarchically related data within a record, such as multiple balances related to a single account, that causes this need for high overhead transactions in the first place. In Couchbase, individual document updates are atomic, so atomicity can be had by isolating transactionally related values within the same document. Or, because we're all about flexibility, for situations where multiple document transactions may be affirmatively required. This feature is supported in 6.5 and beyond. So if you ever want to jump directly into Couchbase and start playing, go to your Settings tab and go to Sample Buckets on the far right. There are 3 data sets available, including Travel Sample. I'll click to load that now. You'll have already done this if you're working in the labs already. If I go over to the Buckets view, we'll see that Travel Sample is in the loading process. I'm going to go over to the Indexes view though, because I want to point out, as I filter here by bucket, that the sample data loads in not just data, but a whole series of pre-built indexes. We'll be looking at how to create custom indexes in the next lesson. I'm going to go over to the Documents view because I want to take a look at what we've got here. I will filter for my Travel Sample bucket, take a look at the first document, and just notice that it does have a type field within it following the design pattern that we recommend. But that's not the document type I want to see. I happen to know that there's a route document that I want to work with. So up here in this Where filter, I can filter for that type because I know it's available in these documents. I'll retrieve my route documents and examine the first one. We'll see that it has fields like an airline code, a destination airport, a distance, and if I scroll down to the bottom, it has a source airport along with type, as we've seen. Now, imagine that we want to do perhaps some fuel analysis, and I want to find all routes with a distance between 1,000 and 1,500. So I'll go over to my query view, and I'm going to select source airport and destination airport along with my airline code and the distance value from my travel sample data bucket. Notice that the query workbench is smart enough to put in the backticks necessary because of the punctuation in that name. But where the distance value is greater than 1,000 and distance is less than 1,500. I'll run that query, and notice it takes 1.28 seconds, kind of an arbitrary number because that would always vary by hardware and configuration. But if I go over to my query plan, we'll see that we're relying on the primary index. What if I wanted to narrow this down a bit to perhaps get better performance? I'll go in and first take a look at my available indexes. We'll go over here and we see that if I filter for my travel sample bucket, what have we got? Airport name, city, FAA code, name and type together. Not quite what I want. Well, at least here there is a type. I could filter all of my documents by type. So let's try working with that. I'll go over here and add in a filter where type equals route, Remember, we had 1.28 seconds here on the performance. I'll execute. Well, it dropped it slightly. And notice here we are now using an index scan of that index that we saw, def type. So that's a little bit better. But what kind of a index might we want to work with here? Seems to me like we'd probably want to have an index that includes our distance value, perhaps along with the type, because we don't have a distance in any of our other documents. In our next lesson, we'll take a look at how to build that and go a little bit further with our index analysis. So what have we learned? JSON flexibly supports typed data, including number, string, Boolean, datetime, geospatial, null or missing values, and multidimensional structures combining any of the above via arrays, objects, and their nested combinations. Couchbase does not, though, support multi-statement transactions. Atomic updates can be had instead by isolating transactionally related values within the same document. Key value create, read, update, and delete operations are immediately consistent across the cluster, while nickel operations are as consistent as you choose to make them on a per-operation basis from the SDK. Optimistic locking is supported with per-document check and set values, and because Couchbase architecture is memory first, write operations are immediately available once made, then written to disk, and optionally replicated within the cluster. Where necessary, each write operation can be optionally configured to confirm when its value has been written to disk and/or replicated within the cluster. Next up, we'll dive a bit further into indexing. Stick around.